In simple terms, what is the difference between quantum computers and conventional computers, and what makes quantum computers so effective for solving complex problems?
Well, to understand the strength of quantum computers, we need to first understand how a classical conventional computer works. And this is simply based on electronic devices, like you have a current or a voltage, which can be on or off, and you can use, for example, electronic devices like transistors, and they manipulate in a logical way the information. So, and that's a deterministic paradigm of calculation. You can always know what you can test and debug, what is the outcome, and such you can calculate. You can process zeros and ones, so the hexadecimal system of numbers, and then you have something like a conventional computer in the end. On the other hand, a quantum computer is completely different. It's a probabilistic scheme of calculation. You make really use of atoms, of orbitals, and orbitals already have the property that you have certain shells. Like maybe we know it, the S and the P shell, only an electron knows where it is today, not today, now, and in a second later. And that's more or less, you don't know exactly where it is, and that's the orbitals. It is somehow uncertain where it is. And we use uncertainty in the direction of, for example, superposition. We are not sure if it is 0 or if it is 1. Somehow it is both at the same time, and that's what we understand as superposition. And that's something completely different than conventional calculations. And there's a second mechanism in quantum computing called entanglement. Now, the Nobel Prize was awarded last year for this, meaning that you cannot describe two systems independently anymore, even if they are light years apart from each other. What does this mean? If you entangle two states, they know from each other. Doesn't matter if there's two nodes in a network, in a neural network, for example, or if you want to teleport information from one point to the other, because simply they know from each other. If you do something at one point, you directly change the other. And that's a strength which also comes from quantum mechanics. It's called the EPR paradoxon by Einstein the other day. So, and these two things, make using of these two things and also operate now, but not also with kind of logical operations with gates. And these gates are manipulations between zeros and one. These are in the end energetic levels, so a ground state and an excited state. But the important thing is that you can manipulate now the entire system, which is uncertain in a superposition. And then you have a very powerful tool to calculate, but it's something probabilistic. So you cannot determine in each time step what's the result. If you want to determine what's the result, then you open Schrödinger's box. The cat is dead or alive. And then you lose your quantum mechanical properties and you go back to the conventional world and the deterministic world. So that's the simple difference, in a sense, is that one is deterministic, the other thing is probabilistic, and we can make use of different concepts, different paradigms, which only consist to the quantum world, like superposition and entanglement.
Could you give a few examples of problems that can be solved much faster on a quantum computer than a conventional computer?
Yeah, definitely. But maybe one comment, quantum is not only about faster. One should have this in mind. It's about faster, so a complexity theory in the amount of gates or operations maybe but also less power consumption, or also more accurate, or anyway possible, something which is classically not possible. But when we think in the direction of faster, or really in speed up, then, as I said, in the post-NISQ era, you can prove analytically that there are certain algorithms with benefits. Thinking, for example, of Shor's algorithm, so you can decompose a large number into two prime numbers very efficiently. And why is this so important? Because this is the basis of our internet encryption, of the RSA encryption. And this you can prove that you can do it exponentially faster, which drives the entire field as a threat, yes, but this has a lot of applications though. So in general, Shor's algorithm or quantum Fourier transformation or quantum phase estimation. On the other hand, there's another very well-known problem which you can solve exponentially faster, which is the so-called HHL algorithm, where you can solve systems of equations, very, very powerful. For example, how they appear in fluid dynamics, for example. but they appear everywhere. So it doesn't really matter where they appear in certain branches in industry, but these two things you can prove analytically that you can get really a quantum advantage, really a quantum speed up, but in the post-NISQ regime. Same as search algorithms for unstructured databases. If you want to find something in a certain database, this you can do also, but only with a quadratic speed up. But this is all known, other examples. But what's not known yet is what can we really achieve in the NISQ era, so today. So what's the direction into quantum advantage with small and noisy systems? Does it work? So we already have some, not yet a smoking gun, but we saw signatures that you can achieve this, for example, in anomaly detection, maybe in image data or also financial data. But there are certain signatures that we can also, everything maybe which has a high configuration space, which you want to search all through at the same time. So the decision tree, for example, which you can shrink down to a branch. This is something which you can do very powerful due to superposition. And there are other things, like if you have, for example, very correlated classical data, maybe you use then quantum correlations, entanglement, to classify or predict. So also there are very powerful tools which you can use here on the quantum side, but this is a heuristic today and not yet proven. But these are all applications, algorithms which we are currently looking at.